Okay, so in this example, in this video, we're going to look at an example of estimating the error on our numerical integration. In this particular case, we're going to use the trapezoidal rule. Now, these formulas for the error can sometimes be given in slightly different ways. The exact value for the error is going to represent some value inside the interval a to b. So sometimes you'll see this formula given in terms of z or some other crazy variable because it's not being evaluated at x per se. It's some value inside that, so they want to differentiate it. But for our estimates, we're not worrying about what's the exact difference between the integral and the value that we estimate. We want to be able to estimate it because part of the goal of estimation is that we want to be able to determine, for instance, in advance, how many step sizes, how many n do we need in order to actually get our integral guaranteed to be within a particular error range. And so we don't necessarily have a value to compare. So we're going to use this general formula, and the error formula depends on the second derivative of the function that we're integrating, and it's also going to depend on the n that we use. So if you've seen the previous trapezoidal rule video, you saw that we estimated this integral log x with n equals 8, and based on the calculator value versus the value that we got, we were somewhere around the 0.01 difference. We had, I think, 6.31, and the true value was closer to 6.32. So we're in that vicinity in terms of the accuracy, and we want to see what the error formula is going to tell us about that. So what we're going to do is we're going to first start by finding our derivative. So f of x is log x. This is the function that we are integrating. And so the derivative of that is going to be 1 over x. And then the second derivative of that is going to be negative 1 over x squared. Now, we are going to find the maximum on the absolute value of this function. So the absolute value of f double prime of x is going to be 1 over x squared. So it does not have the negative sign on it. So we don't have to worry about that. Now, the 1 over x squared function, this is a decreasing function. So if you think about what the graph of this looks like, right, it has an asymptote at 0, but it's positive everywhere. And so as you're going through values that are larger in x, positive values 3 to 7 are the two numbers we're concerned with, but the values are going to be smaller. So since it's a decreasing function on the interval, the largest value is going to be when x is the smallest. Now, if you have a more complicated function, it's entirely possible that your derivative could have a maximum somewhere in the middle of the interval. So for very complex functions, you do need to be very careful about this. A lot of the examples that you will see will have these monotonically increasing or monotonically decreasing examples, and that is not necessarily the only scenario that could happen. If you were looking for a critical point, let's say in between 3 and 7, you would have to take the next derivative and then set that equal to 0 to see where that might occur. But in this case, we have a decreasing function, and so the maximum is going to occur when, in this case, x is 3. So when we put our error together, our error formula together, try to evaluate it, the maximum on this interval is going to happen when x is 3, and that value is going to be 1/9. And again, you can kind of imagine that if you plug in 7, you're going to get 1 over 49, which is much smaller. So 1/9, then we're also going to plug in our values for b, which is 7, and a, which is 3, and n, which is 8 in this case. And then we're going to throw all of that into our calculator. So 1 divided by 9 times 7 minus 3 is 4. So 4 cubed divided by, and again, parentheses are super important here. Both the 12 and the 8 squared, or 64, need to go in the denominator. And what I'm getting is 0.009259 ... And again, this is about what we got last time, give or take some decimal places. We estimated that we were approximately differing by 0.01. And again, without doing all of the extra decimal places, this is about what we would expect the error to be. So that is a good estimate for us. And again, it's about what we saw when we checked our work. Now, the second potential application for this kind of formula is to find the minimum n needed to get a specific kind of error. And so for that purpose, we're going to have a very similar expression here, except that we're going to be looking for, sorry about that. We're going to be looking for n. So what's going to stay the same and what's going to be different? So the first thing is that I am going to use an approximation here rather than an inequality. When we start solving for n and things like that, the n we find should be treated like a threshold value. And so sometimes thinking about it in terms of less than, the inequality will actually need to be n is greater than when we're finished. And so I'm just going to use the approximation sign here to make working with the inequality a little bit less irritating. The 1/9 is still going to stay the same in this case because we are finding it using the same process. We're still working on the same interval. And the 7 and the 3, the A and the B, again, we're still integrating. What's going to change in our denominator is that we're still going to have n squared, and the E is going to get replaced with the error that we are aiming to solve for. Now, what we want to then do is we want to do a little bit of arithmetic. We're going to multiply by 10 to the 5th and multiply by n squared. And so what that's going to get us is n squared. Again, I'm going to use approximately here, just for the sake of simplicity. 7 minus, we'll say 4 cubed divided by 12 times 10 to the 5th. So multiplied by n squared to get it over here, multiply by 10 to the 5th to get that over here. And now I can evaluate this right side of the expression and find out what my n squared needs to be. 1 divided by 9 times 4 cubed divided by 12 times 10 to the 5th. I get approximately 59 to 59.259, blah, blah, blah. And then we take the square root of the result. And remember, in the end, this is a threshold value, so n actually has to be greater than whatever we get here. And I've got 243.43 ... That means that we need to round up to the next whole integer. So n is going to be 244 in order to guarantee that we're going to get this error. Now, again, we've estimated in several places. We've estimated our value for n. We estimated our value for the function. And so this will probably be a little less than the 10 to the negative 5th error, but it is the value that we need to guarantee, without knowing anything else, to guarantee that this will be smaller than this error that we're shooting for.